Okay, let's start our lecture number 18. And until now we have been dealing with fields that are classified as static fields, right? We have the electrostatic field and the magnetostatic field. Magnetostatic field is the one defined in the regime of stationary current. So we have some sort of motion, but it's a stationary motion of carriers, in which divergence of J equals to 0. So now we are going to connect the fields. We are going to allow the possibility of time-varying quantities. So today is the plan. We are going to go through Faraday's law. That's the basic law that makes one connection between electric and magnetic fields. There's going to be a second one, which we already derived in chapter when we spoke about electric conduction. So we have something built in there. But I mean, one important one is Faraday's law. And then after Faraday's law, we can conceptualize, let's just put an apostrophe here. Let's talk about Faraday's law. And then we can conceptualize magnetostatic energy. Even in the magnetostatic regime, to arrive at the energy in the magnetostatic case, we have to use something related to time-varying fields, which is Faraday's law. And then we conclude this lecture, with the theme of inductance. Again, references for this lecture. We have Jackson chapter 5, sections 5, 15, 16, and 17. Just give me 1 second for me to open my notes. Just a second here. So, as I was mentioning, the reference for this lecture, Jackson, sections 5, 15, 16, and 17, and our ebook available in my webpage, chapter 6. The first connection between electric and magnetic fields that was perceived by scientists, that was in early 19th century, was due to Faraday in 1831. And Michael Faraday is one important character in the history of science. I invite you to look into a documentary, or there are several documentaries on the web showing the personality of Michael Faraday. Maybe something like the history. Let me see here what I have here. I think I have one here. On YouTube, you can find a PBS program about Michael. Just look for Michael Faraday, okay? Just search for Michael Faraday. He was the son of a locksmith. Was very simple individual. He didn't have any formal education. He didn't go to college, for instance. And he was studying by himself. He read every book he could read on science. And sorry about this. And he attended several lectures in England when he was young. He was very interested. He took notes, of everything he could grasp. So he just wanted to learn about science. And at the time, scientists knew about Ørsted's experiment, in which you have a wire, right? And you have a compass nearby, and the compass, not like this, but let me make a 3D drawing. So we have a wire. We spoke about that. That the in general the magnetic needle trying to align in an orthogonal direction to the wire. Okay. At that time, scientists didn't have the feeling on the concept of field. They imagined that things happen at the place. I mean, they didn't think that this wire here had an effect at a distance. They didn't understand what would be the connection between these two things. And Faraday had this capability of visualizing things. He imagined that some sort of field of force would act to align the needle. So he's starting to have those ideas. And he wanted to see if, on the other hand, if magnetism would be able to induce an electric current. So it would be the other way around, right? So you have electric currents affecting a magnetic material. He wanted to see if a magnetic material could produce current. That was the effect he was searching for, and he discovered that in 1831. I invite you to watch the documentaries on YouTube. They are very nice. They have in English and in Portuguese as well, and in other languages probably. And you can see the paradigms at that point in time in the early 1900s. Okay, so for our practical cases, we can that's the type of situation. What he observed was that a current would be produced in a circuit if a neighbor circuit would be turned on or off, or if he moved a magnet in the vicinity of a circuit. He could observe a galvanic effect, or in other words, a current on a circuit, by changing the current on one neighbor circuit, or by changing the position of a magnet if you move the magnet nearby a circuit. So he attributed this induced current due to a change in linked magnetic flux. Okay, so in fact, the Faraday's law can be cast if you look into this construction. We now have to pay attention to the change in notation in our notes and in our book as well. Okay, so we are going to change our field notation. We are going to use mostly block letters for DC quantities. I mean, if we have Greek letters, standard Greek letters, or lowercase traditional, in general, but I mean field quantities are generally going to be written like this, and AC quantities are going to be written in a more cursive way. Okay, like those trilled letters shown here. So that's an AC field, that's a DC field. So that's the change in notation I'm going to use. So Faraday's law states that if there's a magnetic flux variation enclosed by a closed loop defined by path C, there's going to be an electromotive force that we call EMF, in fact, in English, right? So that would be an EMF induced, which is going to be defined by this quantity F, capital F, which is proportional to the time of rate of change to the rate of change of the flux, of the linked flux. There's a constant here to be determined. We are going to see that this constant is not arbitrary but has a value. The electromotive force is measured in the reference frame of the circuit. Okay. For instance, if you have a moving circuit, it's going to be measured in the reference frame in which the circuit is stationary, for an observer that is with the circuit. And the flux is a standard, is the flux of B. There is an existing B in the space linked by the circuit. So sigma is the area enclosed by C. And this B is measured in the lab reference frame. That's essentially what Faraday's law is. So the question is, why we have a minus sign here? Well, a minus sign is indicates that the induced current is produced so as the induced field is a linked flux change that opposes the applied flux exchange. Okay, that's in accordance with Lenz's law. So the idea is this: I mean, if you try to put a magnet, try to push a magnet into a loop, no current is going to induce a current such as that the loop pushes away the magnet. So that's the idea. So this the Lenz's law is based on the simple principle that the induced field cannot be produced so as to increase the system energy. So the idea is to avoid the entrance of the magnet in the circuit. So you can see in this diagram, if I try to push a magnet into a loop, it's going to induce this pushing of the magnet is going to induce a circulation of current in the loop, such as the north pole of this induced magnetic dipole is in an opposite direction as the magnet. We know that magnets having the same pole, they repel each other, so that's what would happen. So there would be the prevention of you inserting the magnet. That's what Lenz's law is. So that's the idea, okay? So the idea is that energy cannot be increasing. If you would make something favorable, or in other words, if you would induce something that is aligned along the same direction, that would mean that you'd reinforce the field so that the energy would increase. Okay, so the minus sign prevents an increasing energy in the system and makes some sense physically. Also, there's another important point. K is not an arbitrary constant, and its value can be determined by one very basic simple principle in physics and in natural law. In general, we don't even have to arrive at the relativity theory, but I mean, it's very well common sense that physical phenomena have to be independent on the reference frame in which the phenomenon is measured. If we have different reference frames that move relative to each other with a constant velocity, for instance, it is expected that the physical laws are the same in both frames. Okay, so a simple change in reference frame can be cast according to what's called a Galilean transformation. It's the simplest transformation that there is between different reference frames that have a constant velocity relative to each other. Obviously, this principle is only valid when the velocity is much smaller than the speed of light in vacuum. If we have some velocity that starts to be a reasonable fraction of the velocity of light, then Galilean transformation is, I mean, the invariance under Galilean transformation is no longer valid. Then we have to use a Lorentz transformation, in which we have time dilation and other effects due to relativity or special relativity, as you wish. So, what is Galilean transformation? Well, physical phenomena are the same as measured in frames that transform according to Galilean equations. And this Galilean transformation, let's say, is only, and this principle is only true for a velocity that's much less than the velocity of light. Okay, so we expect that the physical phenomena have the same result in both frames. And we are talking about what's called inertial frames, which are frames which move with constant velocity relative to each other. Okay. In fact, even if one reference frame rotates relative to the other with a constant angular velocity, it's expected that you would measure the same effect. So in this case, you have a constant angular velocity. You don't have a constant velocity vector, but you have a magnitude of the vector is constant in every point of the rotating frame, let's say. Okay? So these are basic principles in which we have to consider, and the value of k is determined by using this constant. Let's look at the Galilean transformation, how it looks like. Just to illustrate, let's put the equations to define the Galilean transformation. You have a reference frame S and another reference frame S prime. Coordinates in S are x, y, and z, and coordinates in S prime are x prime, y prime, and z prime. And assume that S prime and S they have a relative position that's changing with time with a constant velocity. Let's make S stationary and S prime moving with the velocity v, which is constant in any direction, but it's a constant. So I can relate a point in space is going to have a coordinate x relative to S and x prime relative to S prime. Then the Galilean transformation is just the relationship between x prime, and this vector vt. Okay, so assuming that at t equals 0, both origins are coincident, then the Galilean transformation would be simply x prime equals to x minus vt, and the time measured in both frames are the same. Okay, we know from relativity that this is not true if the velocity has a reasonable fraction, or is a reasonable fraction of the velocity of light, so that we would have to have a relationship that takes into account the velocity here. But I mean, for small velocities, we can use the Galilean transformation to prove what's the value of the constant. Okay. So let's assume, just to determine the constant, that we have a loop that moves on a field, as in this geometric construction. Okay, so this is a loop. The loop has an area sigma, area element, differential element the sigma, and normal to that element n. C is the path, and this circuit is moving in a field region described by B field B. Cursive letter, right? Because a B might be changing with time. The velocity is constant, so we can calculate the flux, the time rate of change of flux across the circuit, which would be the time derivative of the flux. We call it psi, and this time rate of change is due to two things. One is because B itself might be changing in time, so we have a time rate of change of B by itself. And the other is because of the velocity. What happens? B might be changing in space. So as the circuit moves in this space varying field, is going to be subject to different fluxes in different space-time, space positions, space locations, right? So even if the circuit is standing, we have a time rate of change of B, and if it's moving, it's going to be this, and also the fact that we have a different variation, different values of B across the space. So I have two effects together. So that's in the sense that the field can change. So what would be the rate of change of B, of the flux, right? So let's calculate. So the flux itself is a function of coordinates, because B changes with coordinates and time, or if you want, x, y, z, t. So the time and rate of change of flux, we have to partial derivative relative to the coordinates, and those relative to time. So that would be a partial derivative like this, dx dt, right? Plus d psi dy, dt, plus d psi dz, dt, plus the explicit dependence on t is going to give me an additional term here, which is the partial derivative of psi relative to t. Well, these are the components of the velocity vector, and those are the components of the gradient of psi. So this can be written as the x dt dot gradient of psi plus d psi dt, and this is the velocity, right? So we have the expression for the flux, time rate of change, which is going to be v dot gradient of psi plus d psi dt. Let's write this in terms of the B field. Okay, just recall that the flux at any point on the circuit is equals to something like this. Integral on the area, which is the sigma. Let's put the normal dot B, the cursive rounded B, right? And recall that this versor here is constant. It doesn't change with time. I mean, the circuit is moving, and the normal is always on the same direction. It doesn't change with time. We are not going to doing this, okay? So if we have rotating things, we have to analyze. But we are talking about the constant velocity field. So calculating the psi dt, is going to be v dot gradient of this expression here. I'm going to put the sigma prime here, okay, just to recall. Let's keep it like this. Notice that the sigma doesn't change in space. The sigma is always fixed to, even here or in different places, the sigma is the same. So this is going to be a gradient of integral B, right? Plus the psi dt. Well, this derivative is only the derivative of the field, so this is going to be surface integral of the sigma n dot dB dt. Okay, so that's what we have. Let's move to the next notes. That's what we have, right? Yeah. So that's what we have. So notice that I could have to figure out what this is, what this thing here is. Okay. So we're going to use some rare vector identity. We never use it, but we're going to use it because this thing is going to look like something that can be identified. So let's look where it comes from. It comes from this identity here, curl of V cross B. This is equals to V times divergence. This is almost a triple, almost like a triple product, okay? This looks like it, but it's not exactly. There are more terms. I mean, if we look at the triple product, A cross B cross C, right? You have A dot C, which is this one, times B, and A dot B times C. So it looks like that, minus, you know, B, which is the third vector, right? Then you have divergence of B, of V. That's what we have, right? Well, that would be if these was standard. If those were standard vectors, we would have something like this: ACB minus ABC. But this is an operator, okay? And so the result is not only that. There are two additional terms. We are going to have two additional terms: minus V dot nabla applied to B. So notice this is an operator, okay? V dot nabla, then you apply that to B. Then plus B dot nabla applied to V. Okay? That's what we got. So for constant V, every derivative of V is going to be 0. So we're going to exclude from this. This is 0, right? This is 0. And also, it is still valid that the fact that the B field doesn't have divergence. So this equation is still assumed valid even for a time-varying field. Divergence of B equals 0. So the only remaining term is this one. So we have a curl of V cross B, in practice, minus V dot nabla applied to B. Okay? So what do we have here? You see that we have the V dot nabla. I can put that, in fact, the thing inside of the integral directly here. Okay? Because this is a scalar operator. It doesn't act on n because n is constant. It doesn't act on sigma. So I can go straight to V dot nabla applied to B. So if we want to see, so the psi t equals to, I'm going to write in a different way, equals to integral of the sigma. Then you're going to have n dot this differential operation, which is V dot nabla applied to B. Okay, so this is going to be a vector, okay? So the remaining is plus n dot dB dt. So according to this identity here, V dot nabla applied to B is curl of V cross B. So we have curl of V cross B plus the other term. This is always on a surface that is enclosed by sigma, that is linked by sigma, the sigma n dot dB dt. Right? So here we can apply Stokes' theorem. This is going to give me, this is the sigma, right? Curl of this vector integrated on an area is the circulation of this field here. Okay? So that's what we have. I think I'm missing a signal, right? Problem, yes. I'm missing a signal. I forgot the minus sign, which was here, supposed to be here. Not yet. No, not yet. This is correct. The sign is going to be in here, minus, because of this identity here, right? So here we have, this is the circulation, minus circulation of V cross B. So if we have this final relation, dip psi dt equals to minus circulation of dl of the vector V cross B plus surface integral of the sigma, put like this, dB dt. So Faraday's law has a minus k in front. So let's put the minus k here. We're going to have here k, right? And here that's going to be a minus k. And this equals to the EMF, right? So let's transport that to the next page. So the EMF, according to Faraday's law, the EMF, electromotive force, which is defined by the circulation of the field in the reference frame of the moving circuit, E prime, okay, dl, equals to this thing here. So I can combine this circulation with this one. So we're going to have something like this. E prime, right, minus k V cross B circulation of this field here equals to minus k dB dt. Okay, that's the result we have. Well, this is what is measured in the framework of the moving circuit. Okay? We have an observer. He notices there's a changing flux due to changing space coordinates at different time points. Even if the observer doesn't see that he's moving, he notices that the field is changing around him. because the field changes in different points in space. So we took that into account. So the moving observer is going to measure this effect, which is going to be here, plus the field that he measured because he's standing in the circle. He's going to measure this field. And it's going to measure a time rate of change of a B field. Okay? So on the other hand, if we went to the lab framework, the fields are simply the field measured in the lab framework and the B field measure in the lab framework as well. And so you see Faraday's law. If you take a picture at that time point, you're going to calculate the EMF due to the field in the lab framework and the B field in the lab framework. You're going to have something like this: circulation of EDL equals to minus K, right? So it just depends on the time rate of change of B. There's nothing moving. It's just at a given point in space, it's going to be changing across that imaginary loop. It's going to have something like this, equals to the sigma dot dB dt. That's what it measures, right? So due to the invariance of physical laws under Galilean transformation, this field has to be the same as this one, right? Because we have that. So we have to have E equals to E prime minus K V cross B, right? Well, so the observer in the circuit framework measures a force on I have a loop which is it's going to measure a force dF prime, let's say. There's a field that it observes. You observe a field E prime, right? It's going to measure a field, a force, dF, let's say, dF prime. So in the circuit framework, observer is going to measure a force dF prime equals to dQ times E prime, right? And in the lab framework, an observer would measure a force which is dF equals dQ times E. There would be two forces, right? One is due to the field, the other is due to the movement circuit. So that it would be a field E plus a particle moving on a field would experience a force V cross B. That's what an observer in the lab framework would measure. So those forces are equal, right? So it means that E prime E plus V cross B equals to E prime So if I move this to the left hand side, means that E plus, here this means that this is equals to E prime because those laws are the same, okay? E prime equals to E plus E prime equals to E plus V cross B. And from the other relation we already showed, E prime equals E plus K VB. K V cross B. So it means that using those relations, there's only one possibility, K equals to 1. So Faraday's law specifies that the time rate of change of flux equals to an EMF induced, unless of a proportionality constant, but this constant has to be 1 due to the invariance under Galilean transformations. So Faraday's law is like this. The electromotive force induced on a closed loop equals to minus the flux, or let's put like this, right? Minus the psi dt. So we have a closed loop, right? And you measure an EMF, which is the circulation of E on the reference frame of the circuit, dl, and the psi equals to the flux of B across the circuits, right? Obvious. So that's what's Faraday's law, right? Obviously, this law doesn't depend on the presence of the circuit. I mean, this is always valid. So if you have in space, whatever, with or without a circuit, no moving circuit, just have in space. If you measure the circulation of E field, okay, now we don't have anything moving, right? Just in space. We have fields E and B. They are connected with this equation. Now we don't have reference frames anymore because we don't have anything moving, any material things, okay? Only when we have material things you have to consider that reference, that E is measured in the reference frame. But now if you have in space, you measure everything in the lab framework, so it's going to be minus the flux. That's the Faraday's law, integral form of Faraday's law. Okay. Sorry about that. That's going to be dB dt. But again, if things are moving, you have to take into account that is the total rate of change of this. Okay. So you have to take, this is a particular case, in space, you have fields E and B. They are connected to this relation. Now, if you have a moving material, then you have to measure the curve, the circulation of the field in this reference frame, and calculate the total flux across the loop. Okay? But in space, E and B fields that are produced by some sources, they are connected by this relationship, which is Faraday's law essentially. Okay. So now we are in a position to determine what is the magnetostatic energy for a given current distribution, right? So suppose that you have a circuit, a DC current I, circulate on a circuit in which the current is sustained by the application of a static a DC voltage V0. Question is what is the energy of the system? What's the magnetic energy? Because current produces magnetism. So we have some sort of energy due to the movement of free carriers. That's magnetic energy, right? So, but I mean, we have to construct this by arriving at this value of currents. And we are going to arrive at this value of current, always maintain the constant voltage. But notice that if I try to change the value of the current, it means that I'm changing the magnetic field linked by the circuit. And that's going to be produce an induced electromotive force, right? So every time I change the current, we have a change in flux that gives me a electromotive force according to this relation. So if you change the current by small increments, delta I, the voltage would change from its original value by an increment F, which is related to di, delta I. So the force, the source has to supply an increment delta V, which has the opposite quantity F, so that it's going to cancel this additional F that arises in the circuit. And this is going to keep the voltage always at V0. So the source will supply energy at a rate which is a magnetic energy, is a power, right? Which is the current that is at that point. The current is I is going to change by a little bit, but at that point is I, times the change in voltage, which is you have to supply to cancel the induced electromagnetic force, electromotive force. And as delta V is equals to minus F, the time rate of change of the magnetic energy is minus IF, and F equals to minus, right? F equals to minus d psi T, which is the electromotive force, equals minus d psi T. So minus IF equals I d psi dt, and this is the basic law upon which we have to calculate the energy of a given state of current. That's the basic expression. Okay, so let's consider on this topic we have a volume in which the current is distributed in this volume. Let's say you have a volume here, right? Have this volume. This volume of currents. So notice that in the stationary current regime, all the currents form closed loops. Okay, so this volume is like a wired, is like a wired circuit. But you have to consider that you have to close the path. Okay. You can consider that this volume is several circuits. It's composed of several circuits, which satisfy the principle of stationary current. In other words, currents are closed loops. Okay. So, for instance, if you have a solenoid, right? You have somehow to close the circuit here. You have a closed circuit there. You can imagine that the solenoid is very packed, so to have several parallel closed loops. So the volume, in fact, are several closed loops, together. That's the volume of current, right? You have a sheet of current on a cylindrical surface, for instance. But always have to remember that the loops are closed. So you have this situation, you have a volume V, Well, you have a volume element, which is delta V, and you have a current that circulates here. I'm going back to the blocked letters, because in the final configuration we are going to have a stationary current, constant field. Okay. So if we look at this volume here can be seen as a sort of microcircuit that has a 3D aspect. Okay, something like this. That's one piece of the volume. You see that you have an element right here which is a volume of this circuit, you know. You have this part here of the circuit. If you look at it, I mean, this, on the other hand, this volume of current is subject to the application of a field, right? I mean, J and B are connected. J produces B. Okay? So, that's this energy we want to determine. So if that's the detail of the volume. The volume has to be some microcircuit that is closed because J is stationary. So we follow that path and then we close the circuit. So here we have a length which is dl, an area, cross section is delta A, lowercase a. And we have a current that the circulating current in this microcircuit is Di. Okay? And we have an element of area in the area enclosed by the loop, which is equals to the S. That's called the sigma, right? The sigma here. So this is a path, right? C. So that's something. It's something like this, right? We have the field. We have all the elements determined. So so just this loop here gives a contribution to the energy. There's going to be a change in flux due to the incremental change in field. We are changing the flux incrementally. We are incrementing the flux by a small quantity. Okay. And only this circuit here contributes to a current delta I. So delta I, the capital delta here, is only associated with the current of that small piece of volume, which is the circuit. And this lowercase delta, Greek letter delta, is due to a change in time of the flux, which is a total change delta phi in the time dt, delta t. Okay? So the energy is going to be the current times delta psi. We can calculate delta psi by integrating on the area enclosed by the loop. And the delta, again, the lowercase delta is due to a time change of the field. The field changed a little bit in time, produces a change delta B. And the flux changed is given by this expression. And this is the current in the loop. Why is a delta? Because it's a piece of the volume. So the delta I equals to the current density times the cross section delta A, which is right here. Okay. So I forgot to put the J here. There's a J right here. So we're going to have delta WB equals to J delta I delta L. But notice that I'm sorry, it was correct. There's no J here. It's delta I. So delta I equals J delta A, but this is delta A lowercase. Delta A. Okay. So equals J delta A. If you plug it in here, this expression becomes this one. And also the flux, let's do it separately here. The flux of a vector B, let's recall this relation here, which is very important. We're going to use it automatically. Equals to the flux of curl of A vector potential, and this equals to the line integral of A, right? Stokes' theorem. So if I use delta B here, it's going to be delta A here and delta A there. So here we obtain that the flux can be written like this, and delta E equals J delta A, so you're going to have this expression. So you see that the volume delta V is equal to the cross section, so right here, times dl. So this small piece of volume, so this is energy of the entire loop. If you want to calculate the energy of only this volume, you just don't integrate here. Just pick delta A times delta L, we call it delta V, and we put the vector on top of J, right? Because the circuit has a cross section that's so small, which is aligned with J. So it's going to be like this. So we have only the, this is the contribution of the entire loop, and the contribution of delta V is a differential of this, which is delta capital of delta lowercase WB, which is going to be delta V, which is delta A times delta L, delta V, times J, times the increment in the vector potential. So this again, right? This lowercase delta is due to a time change of the quantities. Quantities changing in a time delta t. Okay, let's make a time delta t produce a change delta A or equivalent a change in delta B. Right? That's changing time, and that's a piece of the volume, delta capital, the piece of the volume. So there are two differentials here. So that's what we have. So that's the energy change in a volume differential volume delta V, J delta A. Okay? So if you want to calculate the entire energy in one volume element, you see that if you want to calculate the energy change only in the volume element delta V, it's going to be all the change due to the field change from the initial state, which is 0, until the final state, which is AF. Then we have only the energy, let's say, energy density in that piece of volume. If you want to calculate the energy in the entire volume, just integrate in the volume. Then you have the final expression for the magnetic energy due to a field arriving at a final state defined by vector potential AF. So we have to integrate in what is called the space of states. That's an integral carried out in space of states, and a volume integral. And this, of course, we can see that this will be non-zero everywhere where the current is non-zero. J is different than 0, right? That's why it's called the point of view of the source, as we did that before in the case of electrostatics. So just let me outline to you what is this integral here. This is an integral in the space of states, also called space state in physics. Space state, right? So it means that your space is the x's are in the integral, in fact, right? Are the components of the vector. This is not a geometric space; it's a space state. So you go through a trajectory from the initial value of 0 until a final value AF. And along the trajectory, you have to determine what is the function J of A. In general, we know A of J, right? We have to invert that. J as a function of A. We have to determine that. J of A. So at every point, we are going to have a value of J at every point in the trajectory. So this is a line integral in space state of the vector potential A. Of course, we can change this, right? I can change this integral to something that makes more sense. You notice that delta of J dot A, the differential, equals J delta A plus A delta J. So the integral from 0 to AF of J delta A can be cast as this integral here from 0 to the final value JF AF minus integral from 0 to JF of A delta J. Now we have a different integral in the space state of J. This integral here is easy. It's just the final value minus the initial value equals 0. So this is going to be JF AF minus integral in space state of J of A delta J. It's easier to determine the function A of J, right? In a linear system, for instance, we know the response for this. Now, the space state has this configuration here. We change J and calculate A at every point. So we have a space state like this. That's the final value of J. JF, right? Final value. So at every point, you have a line integral now to calculate, which is this one. Now A is a function of J, which is more tangible to determine. And this is given because we know the state, the final state. So we have to calculate this integral here. You can change the integral if you want. So that's the general expression for any system, linear or not. General expression. And if you have a linear system, then things are easier. So why? Because the current density can be written as a continuous variable that goes from 0 to 1, a fraction of the final value, likewise, A is going to be a fraction of the final value. The same, if J is doubled, A is doubled because the system is linear, so we can use the same constant. So we can calculate J delta A. Delta A is going to be a constant. AF is constant. Delta A is delta K times AF. So we're going to have an integral K delta K, right? It's just a change of variables. So if you have J delta A equals to KJF dot delta KAF. Well, this is constant, so it's going to be JF dot AF K delta K, and the energy WB, let's say dWB dV, is going to be integral from K between 0 and 1 of JF AF K delta K, and this integral is K squared over 2, which is 1/2. It's going to be 1/2 of JF dot AF, and the energy in a volume is the volume integral. So I dropped the F index, okay? Not necessary. It's just the actual value of J and A at that state. So that's the energy in a linear system. And again, point of view of the source, okay? As we did before, we can determine this expression in the point of view of the field. So we can do that. We can use the, still we are talking about a DC field. J equals the curl of H. So we can replace J in the expression, right? By curl of H. We don't have 1/2. We just want to have 1/2 when we have a linear system. So we can expand the divergent of the cross product of two vectors. This is a well-known identity. One is a mixed product, right? So if these were standard vectors, we would have just a cyclic property. Only one term. There will be only one term. Let me just recall you. The mixed product has this property, right? A dot B cross C. You can cycle, right? Equals to C dot A cross B, which is equals to B dot A C cross A. So we can always do that if we have standard vector. But when we have an operator, the null operator, we have two terms, right? So it's going to be delta A dot curl of H, which is the cross product between null and H, minus H dot curl of delta A. Okay? So here we have J, right? So this is the term that we have here. Equals to the divergent of the whole cross product plus this term So the curl of A, of an increment in A, is equals to an increment in B. So this term, when it moves to the left-hand side, is going to contribute to this term here. The other one, which is the divergence of this vector, a volume integral becomes a surface integral of this vector here. And notice that the integral is carried out in all the volume that contains a non-zero field. Okay, so this integration is extended to infinity. So we consider here that we have a surface at infinity to enclose all the fields that are produced. So this is one term, right? This is a changing energy, just differential changing B, right? So this is going to be the divergence gives this field. We know that fields fall off for localized distribution of currents, fall off, the potential falls off with 1 over r squared, and fields fall off with r to the third power. So these two terms give r to the fifth power, and the area increases with the square of the radius. So this 1 over r3 r cubed, right? So the contribution of this term here is 1 over r cubed. And in the limit as r goes to infinity, this gives a 0 contribution. So this term here doesn't contribute. So the differential changing energy due to a change in field, delta B, is given to this by this expression. And then you can integrate in the volume. And you're going to have the expression, which is this one, for the energy in a volume. Again, integration is carried out in the space state, right? In this case, in which the coordinates are the components of B, right? There's energy in the point of view of the field now. Energy is carried out everywhere there's a field in the infinite space, or in an enclosed volume if the field is only in that region. So that's the point of view of the field. And again, if I have a linear system, we can use the same argument we used before for the vector potential to show. I can use a k parameter again to show that the energy is going to be given by this simple expression, 1/2 of dVB dot H for a linear system. So just notice the similarity, right? Electric energy for linear system equals 1/2 of dV dE, and magnetic energy, which I'm calling WB, equals 1/2 of B dot H. And when we had nonlinear systems, we had instead, this would be the general formula, would be volume integral, space-state integral, right? And here we have special case of a integral that is in space of states 0 to BF H delta B, right? So there are similar expressions in the E field and B field. Very well. One important concept that is very frequently used in secret theory, in in building transformers, Due to Faraday's law, you can induce current. One circuit can induce current in a neighbor circuit, so you can make windings, and you can link the magnetic field between different windings and induce current and transform voltage from one winding to the other. So one important parameter that arises in this in investigating those situations is the inductance. So let's make a general definition here. The inductance is a parameter that depends only on field configurations and sizes and distances, essentially on the geometry, and also on material parameters. We are talking about fields. We can consider material parameters as well. Suppose we have a set of any current loops in vacuum. Each one has a current I. The nth circuit has a current IN and the path CN, and the capital N is the last circuit in the set. Okay, so this is a linear system. We can calculate the energy using this point of view of the source. Now we see that J are localized current elements. J only exists on the circuits. So recall that JdV, right? JdV becomes, for filamental current, IDL. Okay? So this becomes a sum on the N circuits. We are going to label the one given circuit by discrete variable M. We're going to have two variables, M and N. Let's start labeling each circuit by M. Okay. So we're going to have the IDL, I. So for each circuit, right, we calculate the total vector potential on that circuit. So the argument here is calc A produced by the set of circuits on the mth circuit. So we calculate that, the vector potential on the mth circuit. I think this is wrong. Let me see here. Yeah, this is wrong, okay? So let me just fix it. This is this calculation here is done on the mth circuit, okay? And this is produced by all the circuits, and the coordinate where you calculate it is the mth coordinate. So let me just illustrate here. We have one given circuit. Cm is the path. A location of an element is xm. And this is the differential displacement, which is dl. So we calculate the vector potential of all the other circuits and calculate this quantity, integral, on the mth circuit of dl, vector potential calculated at every point in the circuit, which is xm. Okay, that's what we do. So that's the right way to do it. So xm is the coordinate of a point on the mth loop. So let's notice that, let's just fix here. It's not m, it's cm, right? Cm. Notice that this integral is the flux, right? We did that before. The circulation of A is the flux on the MS circuit. So this is the area of the MS circuit. So the energy is going to be Im times the flux linked by the MS circuit. So it's going to be 1/2 of that. So this is called the flux that is linked to the MS loop, right? So what happens, I mean, if you look here, either the A or B, which is the field, is the total field. Due to the remaining elements of the set. So you're going to have B is the sum. I'm going to use a different discrete variable. It's going to be N now, right? The other loops produce a quantity, including the loop itself. The MS loop also produces a field, right? So the total field is the sum of the fields of the remaining loops and the loop itself, the loop under consideration. So the flux is going to be the sum of the mutually linked fluxes. And if Bn is the nth B field produced by an isolated loop, the flux linked to the MS circuit is going to be given by this expression. Let me see just if this is right. No, this is again wrong here, okay? I have to fix those things. Sigma M, okay? So the field produced by the nth circuit then you integrate on the area of the MS loop. So this is a flux linked by the MS loop due to the field of the nth loop. In fact, you see that this field depends on the current of the loop. So the result of this integration is going to be some geometric factor, which also takes into account the permeability of the medium of immersion times the current In. Okay. So this is called the mutual inductance between loops M and N. You're going to see that this is satisfies a reciprocal property. Lmn and Lnm are the same. So the energy can be written. So we calculate this flux is measuring in Webers, right? I is amps. So this is Weber per amps, which is Henry, the unity of inductance. So the energy can be cast when you write that. So Im times Lmn times In. So that's how we can write it. We can separate for terms m equals n, which is a loop produces a field that is linked by itself. It's going to be a self-inductance, Lmm Im square, plus this mutual inductances here. We have this 1/2 for m different than n. So that would be the expression. I'm going to just show in a couple of instances that Lmn equals to Lnm. So we can call Lmm the self-inductance by Lm, and Lmn we call the mutual inductance. Let's calculate the expression for those mutual and self-inductances. Okay, so let's go. The flux linked by the MS circuit is that due to the nth circuit is going to be A calculate on M due to N. circulation on the mth circuit. The vector potential due to the nth circuit equals to, this is wrong again, okay. Let me just fix here. M calculated on M due to the nth loop equals to integral on the nth loop, right? Cn mu 0 in dln. You see that the nth loop here. And this is being calculated on the mth loop. So the vector is xm minus xn. So that's what this is. So if we plug this expression in here, if we plug this integral in there, we're going to have an integral in Cm, the other in Cn. So we're going to have those two integrals. Mu 0 in the dot product between those two elements. Then we're going to have xm minus xn. So we have to plug now this into this expression here. Let's go back. Well, I think it's back here. Here. Cm is right here, right? So we have to sum on m, on n in fact, okay, to calculate the total flux. So Cmn, okay, so Cmn is the mutual inductance or self-inductance times the current. So it's just divided by In, you're going to have the inductance Lmn, which doesn't depend on the currents, it just depends on the geometry and the configuration. And you can see if we switch M by N here, we have the same result. So we have that reciprocity law, okay? Now notice that due to this property, that's the expression that we have, right? Self-inductance, mutual inductance. Now notice that due to the fact that Lmn is equal to Lnm, and this is a product of two currents, if I switch M by N, I have the same result. So I have two identical terms here. I can group the identical terms together and multiply and sum only once, as long as I sum M equals 1 to N, and N is smaller than M. If I order like this, I can put a factor of 2 in front. So this sum can be written like 2 times this sum here, provided that N is always smaller than M, not larger. I have to fix several things in this notebook. N is smaller than M, okay? So you sum N up to M. Here, I mean, the equal values are separated here. So this for M equals 1, there's no term here. This doesn't contribute. For M equals 2, I'm going to have L21, I2, I1, and so forth, okay? So that's the final expression that we can write for the energy of a set of coupled circuits. You see that the energy depends on the determining the inductances and mutual inductances. Then we have a expression for the energy. Let's conclude the class by looking at this example. Let's calculate the self-inductance of a coaxial cable. Of course, let's assume that the coaxial cable is infinitely long, so you can slice a piece of it and determine the total inductance, or alternatively, you can determine inductance per unit length. So, assuming that the current in the core of the central conductor is uniformly distributed according to this relationship, let's say that Z is coming out of the screen, is AZ is the direction, current per unit area, constant. It's easy to determine the field by use of Ampere's law. Inside of the core, the field is going to be, linear with the distance in cylindrical coordinates. And outside of the core and between electrodes, the field is going to fall off as 1 over r. Let's neglect the thickness of the wall of the grounding electrodes. If we consider that, we have to go inside and calculate the energy that's inside. Let's assume that the permeability of the metal is the same as the vacuum that's outside here. Okay, let's assume that. So I can calculate the energy, which is the energy density is BH, right? So I can calculate and integrate inside of the conductor. There's going to be a part of energy inside and the other part is going to be outside. If you do that calculation, we obtain that the energy per unit length goes with the square of the current. This is the contribution of the inner part of the central conductor, 1/4, plus the log term is that due to the energy outside, which is the other part. So then we can relate this to the self-inductance per unit length of the cable, 1/2 of Li square per unit length. So then we have an expression for the inductance per unit length, which is this is a matter of just canceling the I square, and the 2 is going to cancel that one. So that's what we have. Inductance per unit length equals to this expression, Henry per unit per meter. Internal inductance is this factor here, and the external is this term here. So you can separate the contributions. Internal inductance per unit length is μ0 over 8 pi, and the external inductance μ0 over 2 pi log of B over A. Okay? So that's just an example of how to determine inductance using the basic concept that we derived today. So I think we conclude here. Today's was a little shorter, but that is compensated by the longer ones, right? Longer lectures. So we are going to stop here and hope to see you until next time. Bye-bye.